Welcome to Math with Professor V. In today's lesson, we're going to tackle one of the trickiest concepts in multivariable calculus, limits. Students often find these problems really challenging, not because of the algebra, but because of the concepts behind them. So that's why in this video, I'll walk you through 9 examples step by step, breaking down not just the solutions, but the actual thought process you need to approach them with confidence. Now, this is a continuation lecture, so if you haven't watched the first part, I'll link it in the description so you can start there. Let's dive into the strategies and then work through these examples together. You're going to be doing one of two things, showing a limit doesn't exist or showing it does exist and finding its value. Which of those two you're doing determines your approach, okay? The only reason you should be checking multiple paths is solely to show that a limit doesn't exist. Remember, limits in multivariable calculus are different than the ones that we learned for functions of one variable. When you have a function of one variable, all you needed to check was that the limit as x approached a from the right of a function was equal to the limit as x approached a from the left for a function. And if they were equal, if these two paths were equal, you were good to go. You could say the two-sided limit exists. In Calc 3, it's way more complicated because we have infinitely many paths, not just left and right. So anytime you're checking paths, remember there's infinitely many of them. So your sole purpose is because you already think the limit doesn't exist. You're checking paths to try to show that one path's limit does not equal the other path's limit for the function, and then boom, you're done. I'm so sorry to break it to you, but if you're checking paths, and even if you check 100 of them, or 1,000 of them, or 1,000,000 of them, you still can't say what the limit equals, even if you get the same number every single time, because there's infinitely many, and there's no way for you to check them all. Okay, so then you go, well, Professor V, how am I going to show that a limit exists? These are your options. These are your options. If you think you're actually going to get some constant, some finite value for your limit. First one is direct substitution. Just plug in x and y wherever they're going. Second one is manipulate algebraically, then direct sub. So sometimes when you try direct sub, you get an indeterminate form like 0 over 0, but just with some factoring, multiplying by a conjugate, you fix the issue, and then you can use direct substitution. Another option is the squeeze theorem. Another option is you go polar. You can only go polar as long as x and y are going to 0, 0, which most of the time they are for these limits. And then remember that we have to switch to our approaching 0 from the right side. That's very important. And then the last option is a delta epsilon proof. I don't make my students use delta epsilon proofs in this class unless it was an honors section. So just proceed with caution based on your instructor. Okay? So we're going to jump in. Sometimes the directions are nice and they tell you show the limit exists or show it doesn't exist. I'm just going to be really vague. That way we can go through this journey together. And I'll say find each limit provided it exists. So it could exist, it could not exist. I don't know. My advice to you is, always start with direct sub first, okay? And then we can talk about what to do from there. I know it can be stressful. Okay, find each limit provided it exists. X, y is going to 2, 2, and we have e to the negative x squared minus y squared. Let's just try direct sub. E to the negative 2 squared minus 2 squared. Oh, that's e to the negative 8th. That's a number. That's my limit. Done. Oh, look at that. Not bad. I wanted to start off making us all happy. Okay, next one. Limit xy is going to 0, 0. If we try direct sub here, we'll get 0 in the numerator, 1 minus 1, which is 0 in the denominator. So that's 0 over 0. That's an indeterminate form. Do you know how many indeterminate forms there are? There's 7, like the deadly sins. Okay, so what to do from here? Well, I'm noticing I have this radical quantity in the denominator. Let me try multiplying by the conjugate, see if that makes my life better. So rad x squared plus y squared plus 1 would be the conjugate of the denominator. So let's multiply through by that and then see what unfolds. Maybe cleaning up will allow me to evaluate the limit. Make sure you're writing lim xy goes to 0, 0 every step of the way. The equal sign is on the left of the limit. Sometimes my students put it in strange places. Okay, let me leave the numerator factored because usually some sort of cancellation occurs, so I don't want to distribute. So I'll just have x squared plus y squared times rad x squared plus y squared plus 1. And then since we have conjugate pairs in the denominator, I'm going to get a difference of squares when I multiply it out. So we'll have x squared plus y squared plus 1 minus 1. Do you see that? Okay, great. Well, plus 1 minus 1 cancels. Then I'm just left with x squared plus y squared, which cancels with the x squared plus y squared up top. Oh, this is turning out fabulously. So now we have limit xy goes to 0, 0. What's left? Just square root x squared plus y squared plus 1 plus 1. Okay, now can I use direct substitution to evaluate the limit? Let's see. If I just substitute in 0 for x and y, do I get some number? Why, yes, I get 2, and we're done. So that's our limit. That's our limit. Not bad, right? Okay. Moving on. Limit as xy approaches 0, 0 of x to the 4th minus 4y squared over x squared plus 2y squared. So let's try direct substitution. X and y are going to 0, 0. I would get 0 over 0. That's an indeterminate form. That's not good. Okay, last time we multiplied by the conjugate. Very good. Let me think, can I factor in some way? Look at the numerator. Isn't it a difference of squares? Yes, so you might be getting excited going, this is x squared plus 2y, x squared minus 2y. Oh, yay. Will that cancel with something in the denominator? Womp womp. No, it won't, because this is 2y squared. Oh, shucks. Okay, so then what do? Well, you have a few options. In this case, I would say you could try switching to polar. We'll talk about that in another example. Or you could test paths. This is a common thing. Now, since I'm testing paths, I suspect the limit does not exist. So I'm not trying to show it equals some value. I'm trying to get two different values from testing the limit along two different paths. So let's try testing what the value of the limit is along x equals 0, along the y-axis. So now we're going to have the limit as 0 comma y approaches 0, 0. So I'm just substituting in 0 for x. And then again, I'll substitute in 0 for x into this expression here. So we will have 0 minus 4y squared over 2y squared. Okay, now what you need to do from here is simplify this expression. Don't get so excited that you start plugging in 0 for y, because you're just going to get an indeterminate form again. But if I simplify this expression here, y squared cancels, and then negative 4 divided by 2 is negative 2. So you always clean all that up first, and then you go, oh, I'm left with negative 2. And so it doesn't matter where these are going, this is a constant, and the limit of a constant is always just itself. Okay, so that's the value of the limit along x equals 0. Let me try switching it and go along y equals 0, x-axis, and see. Hopefully I get a different value. So x0 approaches 0, 0 of x to the 4th minus 0 over x squared plus 0. Remember, clean this up first, then you try to substitute. Clean up first. So this is the limit as x0 approaches 0, 0. X to the 4th over x squared simplifies to x squared. Now substitute in, x is approaching 0, so this is 0. Oh, perfect. I got something different. So you can say, since different paths yield different limits, then the limit as xy approaches 0, 0 of x to the 4th minus 4y squared over x squared plus 2y squared does not exist. Okay? So this is kind of the same as when you got a limit from the left not equaling the limit from the right in Calc 1, and you were like, oh, the limit doesn't exist at x equals a. So we've just shown two paths that don't have the same limit. But you know, you don't have to necessarily go along linear paths. You could go along parabolic paths. You could go along any sort of path. And another kind of slick way to check general case for all linear paths is you can test along y equals mx. So I'm going to redo this problem that way, okay, just to show you some options. It's pretty snazzy. I like doing it. Anytime I can kind of make the process more succinct and efficient, I love it. Okay. So in this case, we're approaching 0, 0. I'm going to go along a general linear path, y equals mx. So obviously this would not apply for vertical lines. This is just along any line where the slope is defined. And we can see here, if x goes to 0, y is equal to mx. So that means y would be going to 0 as well. So this is an appropriate path to choose for this limit. So we're going to look at the limit as x mx goes to 0, 0. And then now substitute in mx for all the y's. So we'll have x to the 4th minus 4 mx squared over x squared plus 2 mx squared. Are you good? Okay, so then this is the limit as x mx approaches 0, 0. And we have x to the 4th minus 4m squared x squared over x squared plus 2m squared x squared. And then clean up. You see how I can cancel out an x squared from everybody? Yes, Professor V. Oh, good. Okay, so then we're going to have x squared minus 4m squared over 1 plus 2m squared. Perfect. Now, x is going to 0. X is going to 0. So this is going to 0. M times x is going to 0 because x is going to 0. But that's all I can do. So I'm left with, these are constants now, negative 4m squared over 1 plus 2m squared. So what does that tell me? Oh, I didn't want that. I wanted to box it. Well, this tells me the value of the limit is dependent on what? On m, the slope. So different linear paths will yield different limits. Therefore, the limit doesn't exist. I don't feel like rewriting it. Copy paste. Now, are you ready? Something dangerous I need to tell you. Dangerous. What if I got a number? What if I got a number like 4? Could I say the limit exists and it's 4? No, 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 no. Because in this case, we just checked for a general linear path. There's infinitely many paths. They don't all have to be linear. So again, when you're testing along y equals mx, the only way you actually can finish the problem and get a conclusive result is if it's dependent on m and you say the limit doesn't exist. This will never help you show a limit exists or what it's equal to, okay? Path testing is only to show the limit doesn't exist. And if after a while you're testing paths, and you keep getting the same number and you go, man, I'm really thinking the limit does exist, it's got to be this number, then you got to shift gears. Then you go back to one of these strategies here. Path testing is only to show a limit does not exist, okay? Good, good. Let's get back to where I was. Here we go. So limit as xy approaches 0, 0, y squared sine squared x over x to the 4th plus y to the 4th. Why don't you pause the video, try this one on your own, okay? It's good practice for you. Okay, I hope you paused it. So if we try direct substitution, we get 0 over 0, so that's not working out for us. Now let's try some paths. Let's go along y equals 0. Great. So we'll look at the limit. 0y approaches 0, 0. If I have y equals 0, I have 0 in the numerator over x to the 4th. Remember, always simplify first, then worry about evaluating the limit. So 0 over something that's not 0 is 0. And then the limit of a constant is itself. Okay. Now say you tried next the path along x equals 0. Okay, let's see. Along x equals 0, we're going to have the limit as 0y approaches 0, 0. I'd have y squared times sine of 0 over 0 to the fourth plus y to the fourth. So that's the limit. 0y approaches 0, 0 of 0 over y to the fourth, which again, that's the limit. Simplify first, then evaluate the limit. So 0 over y to the fourth is 0, and limit of a constant is itself. Oh, I got 0 again. Does that mean the limit's 0? No, I hope you were yelling over there. No, it's not, right? We're checking paths. This is only to show the limit doesn't exist. So what do you think? If you're thinking it's 0, then you should do one of the other things. You should stop testing paths. But I'm going to try one more path, you guys. I'm going to try along the path y equals x. And you might say, Professor V, what's making you think to do that? You know, I've just practiced enough of these, okay? So then you start building some pattern recognition and intuition. So along y equals x, I'm going to have xx goes to 0, 0. And I'm really picking this path because, look, you see how these are to the same power? I feel like I can clean up and manipulate. If I had 2x to the fourth down there, that would be x squared. I see a sine squared. I'm feeling like I can play around with this limit and squeeze something other than 0 out if I make this substitution. That's where my mind's going, to be perfectly honest. So x squared sine squared x over x to the fourth plus y to the fourth. Okay, so we know this is going to be 2. What did I do? I meant to put an x there. That was silly. 2x to the fourth. So then now we have limit xx goes to 0, 0. And then we have x squared sine squared x over 2x to the fourth. And then x squared cancels. So now this is x squared. And then hopefully you remember from Calc 1 that the limit as theta approaches 0 of sine theta over theta is 1. Very good. So then I'm going to use that now. Let's rewrite this limit. This is the limit. Xx goes to 0, 0. I have this pesky little 2 down here. So let me write it as 1/2. And then we have sine squared x over x squared. But really, this is just sine x over x, quantity squared. And we just said sine theta over theta goes to 1. So sine x over x will go to 1 as long as x is going to 0. So that goes to 1 squared times 1/2. So this is 1/2 times 1, which is 1/2. Hallelujah. We finally got something other than 0. Do you see that? These were zeros. We got a non-zero number. Perfect. So since these are not equal, then we can say the limit as xy goes to 0, 0 of y squared sine squared x over x to the fourth plus y to the fourth does not exist. Woo! Very good. How you guys doing? Okay. Let's move on. Here we have the limit as xyz approaches 0, 0, 0 of xy plus yz squared plus xz squared over x squared plus y squared plus z to the fourth. Okay, so obviously if we do direct sub, we're going to get 0 over 0. I don't see any factoring I can do. I don't see any multiplying by conjugate I could do. Let's test paths. But you know how I showed you in the previous example, you could go along a general linear path, y equals mx. Let's extend that to 3 space. So how do we represent a line in 3 space? Well, it would have a direction vector, right, with components a, b, c. And in this case, since we're going to the origin, the fixed point on that line would be 0, 0, 0. That's my x naught, y naught, z naught. So if you were to form the parametric equations for a line with arbitrary direction vector, think of this as equivalent to having arbitrary slope m. We would have the following parametric equations: x equals at, y equals bt, and z equals ct. And we can see here, as t goes to 0, where does xyz go? Very good, to the origin. So let me make this substitution. Let's test along a general linear path in 3 space and see what emerges. So we're going to rewrite this now as the limit as t approaches 0. X times y would be at times bt plus yz squared, bt times ct squared plus xz squared, at times ct squared over x squared plus y squared plus z to the 4th. Okay, then we clean up. So limit t goes to 0, abt squared plus bc squared t cubed, yes, plus act cubed over a squared t squared plus b squared t squared plus c to the 4th t to the 4th. Okay, what can I cancel out? T squared from everybody, right? So this is limit t goes to 0, ab plus bc squared t plus act a squared plus b squared plus c to the 4th t squared. Whew. Okay, now let's go ahead and take the limit as t goes to 0. So a, b, c are all constants. Any constant times 0 will go to 0. So I'm left with ab over a squared plus b squared. Well, what does that tell me? Well, just like in the last problem, the limit was dependent on m. Therefore, different linear paths yielded different limits, so the limit didn't exist. So again, we can say the same thing here. Since this limit is dependent on what? On a and b. But what are a and b? Those are the components of the direction vector, right? So since the limit depends on the direction vector of the line, we can say that different paths yield different limits. Therefore, the limit doesn't exist. Let me rewrite the original. You know, I always rewrite the original at the end. I had very strict professors in my day who just would not give full credit unless you rewrote the original. So it's ingrained in me. I'm just thankful for technology now. Okay, good. You know why this is so hard for students? I'll tell you why right now. Because there isn't like a one-size-fits-all procedure that you can use. Nope, you gotta think. Okay, here we go. Xy goes to 0, 0, xy squared cosine y over x squared plus y to the 4th. Oh yeah. So again, if you try direct substitution, you get 0 over 0. Let's try some different paths, yeah? Let's try along, what do you want to do? X equals 0, y equals 0, doesn't matter. Let's try one of those. Maybe you can start checking in your head some of them, yeah? So along x equals 0 would be 0, y goes to 0, 0. We would have 0 in the numerator over 0 squared plus y to the 4th. Remember, always simplify this expression first. So this is the limit. 0y goes to 0, 0 of 0, which is 0. Okay, if you check along x equals 0, you will get the same thing. So then you go, all right, we're going to have to try a different path. Should I try along y equals x like Professor V did last time? No, that won't help you. So here's where you got to spot the difference. You see how this one had x squared, and then y to the 4th? Okay, go back to the other one I did. Where was it? This was x to the 4th, y to the 4th. They were to the same power. So then I got to combine like terms and then cancel and do some stuff. So you look at this and you go, all right, I really wish these were to the same power. So I'm going to have to maybe substitute x equals y squared. Then that would make this y to the 4th. Maybe I can clean up and do something snazzy. All right. So let's try. This is a nonlinear path. Look at us upping the ante. Along x equals y squared. Here we go. So we're going to look at the limit as y squared y approaches 0, 0 over. So now replace all the x's with y squared. So I've got y squared cosine y, y to the 4th plus y to the 4th. Guys, this is 2y to the fourth. This is y to the fourth. This will cancel with this. Just leave me with the 2 downstairs. Oh, this is working out fabulously. Y squared y goes to 0, 0. Cosine y over 2. If cosine y is going to 0, cosine of 0 is 1, so we get 1/2. Boom. We got a different number already. So what does that tell me? That the limit does not exist. Check with your instructor how they want you to summarize. Maybe I'm being overly paranoid. Does not exist. I would just say not equal and draw an arrow to each, which implies the limit doesn't exist. Okay, hopefully you're getting the hang of it. Let's look at this one here. Limit as xy goes to 0, 0, and they're telling us x is different from y. That way you don't have to worry about the denominator being 0. If you try direct substitution, you get 0 over 0. This one looks scary. I don't want to try to check paths, right? Let us factor. Notice in the numerator we have 4 terms. We can factor by grouping. So let's take out the greatest common factor. 2 terms at a time. So xy is going to 0, 0. 4 rad y and 4 rad x have 4 in common. So then I'm left with rad y minus rad x plus, now the key here is remembering you can express x as rad x times rad x. So I can factor out rad x from both of these guys. And then I'm left with rad y minus rad x. Ooh, so snazzy, right? Okay, then let's fully factor the numerator. You could cancel now, but I don't trust some of y'all. So we have rad y minus rad x times 4 plus rad x, yay factoring by grouping, over rad y minus rad x. Then this will cancel, and we have the limit as xy approaches 0, 0 of 4 plus rad x. So this will be 4 plus rad 0, which is 4. Done. Yay. Notice I didn't check paths. I got a value. We just did some manipulation. Okay, I got a couple more for you. Limit as xy goes to 0, 0 of 9xy over the square root of x squared plus y squared. So one of the techniques we haven't gone over so far is switching to polar. So when you go to polar, oh, there's my alarm. I'm awake. When you go to polar, you're going to substitute in x equals r cosine theta, y equals r sine theta, x squared plus y squared is equal to r squared. And you can only do it when you're going to the origin, and make sure that you state that r is approaching 0 from the right, because r won't be negative. This is often very helpful, and you can show a limit exists when you switch to polar. You can also use a lot of your limit techniques from before, like L'Hopital's rule and stuff, when appropriate. So let's try that on this problem here. I'm going to rewrite this as the limit. As r approaches 0 from the right, 9xy would be 9 times r cosine theta, r sine theta, over square root of x squared plus y squared is r squared. Okay, this is just going to simplify to r. I don't need absolute value because r is going to 0 from the right. So let's see what we've got here. Limit, r goes to 0 from the right. Up top I have 9r squared cosine theta sine theta over r. So one of these r's will cancel. And then now we have the limit as r approaches 0 from the right of 9r cosine theta sine theta. Well, let's see. I know r is going to 0. What about cosine theta times sine theta? I don't know. All I have info on is that r is going to 0 from the right. But I do know that cosine theta and sine theta behave. I know they're not going to infinity. That's a concern of mine because 0 times infinity is an indeterminate form. When I say they behave, I mean they're bounded. So really what we need to do now is the squeeze theorem. So I'm going to say, I know cosine theta times sine theta is always between 1 and -1. I mean, we could be precise, more precise, say that's 1/2 sine 2 theta. So therefore, yeah, we could bound it better, but it's okay. This is good enough for our purposes. So from here, remember when you're doing the squeeze theorem, you want this quantity that's bounded to match whatever you're trying to find the limit of. So I'm going to come through, multiply everything by 9r. And since r is approaching 0 from the right, I know it's positive, so the direction of the inequality is preserved. So I have negative 9r is less than or equal to 9r cosine theta sine theta is less than or equal to 9r. And then from here, this is where the beauty of the squeeze theorem comes in. We take the limit of a much simpler function, r going to 0 from the right, of negative 9r. That's 0. And that's the same as the limit of the upper bounding function. And therefore, I can say that the limit as r approaches 0 from the right of 9r cosine theta sine theta equals 0 also. And you have to cite your sources by the squeeze theorem. I actually just made a little squeeze theorem video for Calc 1. If you need to check it out, do so. So that's it. We got a number. The limit's 0. Could I have gotten it testing paths and getting 0 every single time? No. How many paths are there to test? Infinitely many. You won't ever make it. So if you think a limit exists, you got to do one of the things from the second column that I listed at the beginning of the video. Okay? Let us look at this example here. This is the grand finale. We have the limit as xy approaches 0, 0 of e to the negative x squared minus y squared. That's all in the exponent. And then minus 1's not in the exponent. That looks kind of confusing. Over x squared plus y squared. So I picked this one because, yeah, I did want you to go polar. Okay? Let's do it. So here we go. We're going to have the limit as r approaches 0 from the right, e to the, this is negative x squared plus y squared, right? So e to the negative r squared minus 1 over r squared. Okay, let's try direct substitution. That would be e to the 0 minus 1 over 0. Uh-oh, that's 0 over 0, right? Oh, but I can do L'Hopital's rule when I have 0 over 0. This is exciting. So we have limit, r approaches 0 from the right. L'Hopital's rule is the illegal quotient rule. You just do derivative of the top over derivative of the bottom. So derivative of e to the negative r squared is e to the negative r squared times negative 2r. And then derivative of the bottom is 2r. They cancel. And then I'm left with limit r approaches 0 from the right, negative e to the negative r squared. And then can we use direct sub? Yeah, this is negative e to the 0. So the result is negative 1. Boom. Very relaxing. Students love switching to polar. They do. And you can actually do it on some of the earlier examples where we were testing paths instead. Shall we revisit one of them? I think we should. Give me a moment. Let me find one where it would be nice. We didn't switch to polar, but we could. Let's do this one. Let's revisit this guy. So limit xy goes to 0, 0 of x to the 4th minus 4y squared. I'm just going to squish it in right here. I just was thinking you could go polar and get the same result. So let's do instead limit r goes to 0 from the right. X to the 4th would be r to the 4th cosine theta to the 4th minus 4y squared is r squared sine squared theta over, now x squared plus 2y squared, look how slick I'm going to be. X squared plus 2y squared is x squared plus y squared plus y squared. So this is r squared plus r squared sine squared theta. You see that? Wow. Okay, I can cancel r squared out from everywhere. So limit r goes to 0 from the right. You're going to have r squared cosine to the 4th theta minus 4 sine squared theta over 1 plus sine squared theta. Now as r goes to 0 from the right, this term's going to go to 0. And then I'm left with negative 4 sine squared theta over 1 plus sine squared theta. Notice I didn't get a number. I cannot use the squeeze theorem. I can't bound this. So, because this could approach 0, which would mean the whole thing could approach infinity. And you notice how it's dependent on theta. It's dependent on theta. So that's it. That's the same as saying the limit depends on m, basically. Limit depends on theta. So different paths yield different limits. Therefore, the limit doesn't exist. Am I rewriting the whole thing? I sure am. It's ingrained. You guys, I just like, bothers me not to. I wish it wasn't this way. Okay, whew, we got it. Do you like that better? You know, my students love going polar. They love it because it's a little, they like to just kind of zone out and just do one process over and over. Isn't that terrible? Okay, let me know if this helped cleared up some cobwebs, because I know this is a very difficult topic. If you want more examples, because you know, we didn't do the squeeze theorem, but I feel like I didn't want to go on and on and on. So comment down below. Do you want a part 2? Is there a particular kind of problem that's tricky? I can do so much more. And I appreciate you guys watching. Make sure, check out the first part of this series and then my other calculus playlist, because I have full-length video lectures on Calc 1, Calc 2, Calc 3, linear, differential equations, so much more. And don't forget to like, subscribe, share this with your classmates who are maybe struggling with limits also. And you can follow me on Instagram and TikTok, Math with Professor V. I'll be back sooner than later. Bye, guys.